Hi guys, welcome to Close House Mathematics class. Don't forget to subscribe, like and share this video. In today's class, we want to talk about vector space. When do we say a vector is a vector space? Now, what is the definition? The definition states that let F be a set on whose two operations, vector addition and scalar multiplication, then V, that's the vector V, along with two operations, is a vector space over a field F if it satisfies the following conditions. So if we are told to define a vector space, there are 10 conditions that must be satisfied for it to be a vector space. So the first one is additive closure. So this says that for every, so this sign means for every. So you can call this for every, or you can say for all. So when you see this sign, it means for every or for all. Then if you see this sign, so let's just make some notation. It means belonging to. So this means belonging to. Are you seeing that now? So if I say this now, I can say for every u and v belonging to vector v, my u plus my v should also belong to vector v. And the second one states that the second one is called commutativity. Commutativity deals with two vectors. Are you seeing what I'm saying now? So this says that for every u and v belonging to v, my u plus v should be equals to my v plus u. The third one is associativity, which is for every u, v, w in my v, my u plus my v plus my w should give me the same thing as my u plus my v plus my w. The third one is the additive inverse. This one says for every u belonging to v, there exists. So this sign means there exists. So when you see this sign, it means there exists. Are you seeing that now? So there exists minus u in v, such that, so when you see this sign, it is the same thing as such that, all right, such that u plus minus u should give me 0. We are going to be seeing the use of all this in an example. Then the fifth one is called zero vector. This one says if there exists 0 in v, such that u plus 0 should give me u, which should also be in my what? In my v. Normally, we all know that if you add 0 to anything, it should give you that same thing back. True or false? True. Then the number 6 is called the scalar closure. Scalar closure. Now, one thing about scalar is that it deals with, if you don't forget, we said a vector along with two operations is a vector space over a field. So that field is this scalar. I get what I'm saying. So when we talk about scalars, we are talking about the field. So he said if there exists a scalar f, and that scalar can be anything. I get what I'm saying. It can be any constant. So you see, if there exists a scalar in vector in field f and u in vector v, then alpha u should also be in what? In my v. The seventh one says that scalar multiplication associativity. Don't forget, I told you that associativity deals with 3, commutativity deals with 2. Like you can see here, the associativity is dealing with u and v, but commutativity is dealing with u and v, and associativity is dealing with u, v, w. So here we talk about scalar multiplication associativity because we are talking about scalar multiplication, and multiplication occurs between two things. That means you automatically know that I'm going to be having two scalar here. So it says for every alpha and beta in field F. So F is a field. F is a field. Are you seeing that now? F is a field. So for every alpha and beta in field F and U in V, alpha multiplied by beta U should give me the same thing as what? Alpha beta multiplying what? U. This is a normal multiplication. Are you seeing that now? The number 8, it is called distributive across scalar addition. Now I want to make a similarity between this number 8 and number 9. This one says distributive across scalar addition. Now we know that addition deals with two things. So because we say scalar, are you seeing that now? That means you are going to have two scalar adding each other, then multiplying what? U, which is giving us this. Now look at the ninth one, which is vector addition. You can see that here now I now have two vector and one scalar. Are you seeing that now? I have two vector and one scalar, which is now giving me alpha u and alpha v. But here I'm having alpha u and beta u. You see that now? So that is some of the ways to remember some of these theorems. Then the last one here says that the existence of one, and this is talking about one. That is, if there is, for every u in V, 1 multiplied by u should also give me what? My u, which should still be in my V. It is as simple as that. So we have 10 axioms. Now these 10 axioms are subdivided into two. The first 5 are called the additive law, while the other one are called what? The multiplicative law. And we are going to notice something, that from these first 5, we are only dealing with addition, 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 addition. But when you come to this 6 to 10, you are seeing multiplication, 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 multiplication. So those are the ways to remember some of these things. Now we want to see an example on this vector space. So when do we say something is closed under an operation? So that is what we are going to be seeing in the next example. So don't forget to subscribe, like, and share this video. So let's go into example now. So our example, we have, they say given that A equals a set -1, 0, and 1. Then I say show that A is closed under the operation addition. Now, for us to show that A is closed under the operation addition, it means that we have to show that A is additive closure, it is commutative, it is associative, it is additive inverse, and it is a zero vector. If these 5 things are satisfied, then we'll say that A is closed under the operation. So the first thing you need to know is that this will be your U, this is your V, and this is your W in all the notations we have used before. Are you seeing that now? So let's begin. The first one, which is the additive closure. Additive closure states that for every U, V in V, U plus V should also be in what? In V. Now let us check. If you are checking, this is U, this is V. That means if I add these two together, the answer I should get should also be in my A. Because this our V here is the same thing as our A here. I get what I'm saying. So I can say that for every -1, 0 in A, are you seeing that now? -1 plus 0 should also be in what? In my A. So let's check. -1 plus 0 will give us what? -1. Is -1 in my A? -1 is in A. Therefore, it is satisfied. Are you seeing that now? That is satisfied. Number 2. So this is number 1. Number 2 now. Number 2 is commutativity. Commutativity states that for every u, comma v in v, comma, my u plus my v should be equal to my v plus my u, which should also be in what? In v. Let us check that. So that means we can see for every, if you are checking that here, we can see for every minus 1, comma 0 in A, minus 1 plus 0 should give us the same thing as 0 minus 1. So let's check. Minus 1 plus 0 will give us what? Minus 1. And 0 minus 1 will also give us minus 1. So therefore, minus 1 equals minus 1. And you can see that minus 1 is still in my what? In my A. And minus 1 is in my what? Is in my A. Therefore, it is satisfied. Are you get what I'm saying now? Now, number 3. Number 3 is associativity. Associativity is dealing with 3. Don't forget I told you associativity for every u, v, w in v, u plus open bracket v plus w should give us the same thing as open bracket u plus v plus w, which should also be in my what? In my v. So let's check that. That will be what? If you are checking that, so we already know the notations as I'm writing them. So that means minus 1 plus 0 plus 1 should give me the same thing as, so I've written this first, should give me the same thing as minus 1 plus open bracket 0 plus 1 plus 1. So let's check that. That will give us minus 1 plus 0 is minus 1 plus 1. And that's the same thing. This is minus 1. 0 plus 1 will give me 1. And this is giving us what? 0 equal to 0. And you know that 0 is still in my what? In my A. Satisfied. Are you seeing that now? Now, the third one, the fourth one now is what we call the additive inverse. An additive inverse says that for every u in v, for every u in v, sorry about that, for every u in v, there exists minus u in v such that u plus minus u should give me 0. Now, you know that our u here is minus 1. So if I use it, so this is minus 1 plus minus 1. Are you getting my notation now? Are you seeing my notation? You know, this is my u plus this minus that is in the formula and then my minus u again. I get what I'm saying. So that will be minus plus minus and minus should give us, so this is giving us minus 1. Minus and minus will give me plus, multiply by plus, so that's plus 1, which will give me what? 0. You can see that it has satisfied the law, which says that it should be equal to what? It should be equal to 0. So it is equal to 0 already. And what do you notice? 0 is still in my what? In my A. Certified. Are you getting that now? So 0 is still in my A. That means it is what? It is certified. Then the last one now, which is 0 vector. The last one now, 0 vector. That one states that what? Very simple. It states that for every, it said if there exists 0 in V, if there exists 0 in V such that u plus 0 should give me what? My u. Normally. So what's your u? Your u here is what? Minus 1. So minus 1 plus 0 will still give you what? Minus 1, which is still in what? In your A. Therefore, it is satisfied. Now, what do you notice? You can notice that the first one is satisfied, second is satisfied, third is satisfied, fourth is satisfied, and fifth is satisfied. Therefore, so you can now conclude and say, therefore, the set A is closed under operation what? Addition. So with this, you will be able to get your full mark. So I believe that with this few explanation, you've been able to understand what we see when we ask you to do vector space, and when you are being asked that a vector is closed or not. So these are the way you are going to be doing your examples in your exam. So don't forget to subscribe to this channel, like and share this video. In my next class, I'll be talking about vector subspace, and we are going to be seeing how to solve questions on subspace. So if you have not turned on your notification, do that, and see you in the next class. Thank you very much, and do have a great day.